Hello, my name is UTKARSH and I will be giving presentation on the topic sampling continuous time signal. The content of this presentation are as follows. We will begin with introduction. We will discuss about the basic definition of sampling and why do we need sampling, and further we will continue discussion about the sampling frequency, which is very important in our operation, sampling operation. Continue discussion in sampling in time and frequency level and how they both are related and how both are equal in some way or other. And then we will continue discussion in conditions for sampling, and then we will discuss about the overlapping and how to avoid it, and we will write the MATLAB code for our sample signal to better visualize our sampling process, and then we will conclude with summary. So moving forward, so basically sampling operation means of obtaining the digital signals from the continuous time signals. Okay, now the question arises, why do we need the sampling process? Okay, the answer is that for all the digital devices that we use nowadays, they take the input in the form of discrete signal or either the digital signals. Okay, but all the real signals are continuous signals, so they can't be directly processed to our devices. So in order to manipulate our devices, we need to use our sampling operation, which will convert continuous into digital signals. Now for digital signals, it can be related to the continuous signals in such a way that we can represent in such a way that for amplitude values taken for continuous time signal at every multiple steps or multiple values of sampling period, we can find a data signal for that particular continuous time signals. Okay, we will discuss it further next. Now for now we will see how in this discussion we will use the Fourier transform representative of discrete time signal to analyze the sampling process, and at the last we will also see the verification of our sampling process by the DTFT or sampling process, by relating the DTFT sampling process to the Fourier transform of our continuous time signal. Moving forward, discussing about the sampling frequency. The sampling frequency is one of the major or most important parameters in communication theory. Okay, so definition goes as follows. Sampling frequency basically shows number of samples taken from continuous time signals per second. By an example, we can elaborate it in such a way that, for example, 1000 Hertz for every second, we get 1000 samples are taken from that particular continuous time signals. And further we will discuss how the sampling frequency we will decide which signal will be sampled or not, and how overlapping leads to the mismanagement of sampling frequency. For now, let us continue discussion by considering x of t as our continuous time signals and x as discrete time signal. As we have previously stated, that we can devise the correlation between two by taking the periodic sampling of continuous time signal at integer multiple value of sampling period ts. This can be elaborated graphically in this way. For example, for sine curve, we have taken the instantaneous value at integer values of sampling period. By this we can store it in the form of array, then we can plot it in MATLAB, okay, as a graph in discrete signal. Okay, now message signal is our signal which we will use to which we will use for sampling. Okay, this is the graphic representation of the continuous time signal. Okay, so one of the basic condition or the important condition for this signal so that it should undergo sampling is that it should be band limited with the non-zero frequency omega n. Okay, now the omega n can be calculated by performing the Fourier transformation on this signal, which will obtained in this way. Okay, for this transformed signal, we can see that omega n represents the highest non-zero frequency. Also, one more condition is that the frequency content for this xt or a continuous time signal should lie between this particular frequency range only, that is this particular frequency, for the purpose of sampling. Okay, so also as the sampling theorem state that the conceptual content of sampling state that to reconstruct a sampled version, we should avoid the frequencies which are greater than this highest non-zero frequency of our continuous time signal. Okay, it should be avoided so that our reconstruction should be done easily. Okay, now period impulse train. Period impulse train is one of the is one of the signals which we will use in time domain in order to obtain our sample signal. So it should be represented in this way, where ts is the time is the fundamental time period. Okay, and omega is our sampling frequency. And the first step toward the time domain is the multiplication. We need to multiply our continuous time signal with the impulse train st. Okay, now to begin with multiplication, we will substitute the value of st as we have previously obtained in our discussion. Okay, it will be a modulated impulse. Okay, so by the impulse sampling of our signal with the impulse train, we get this sort of graphical representation. This is our xt, continuous time signals, which can be any signal, and st is your impulse train. And after sampling it, we obtained this one, and we can see we can obtain sampling at every instantaneous value of this impulse train. Now we can also elaborate it is that the sampled signal can be viewed as a impulse shifted version of continuous time signal at particular interval Ts. Okay, now this equation can further be elaborated as such by considering the impulse function property, this one. Then we can elaborate it in this way, and after substituting the value between discrete and time continuous time, we will have our this final equation for a time domain. Okay, now if one want to calculate the weight of the impulse in the sample signal, he or she can do so by taking the instantaneous value of continuous time signal at a particular sampling frequency period. Okay, now sampling in frequency domain. Okay, now we have discussed the sampling frequency, how it is important in this sampling operation. So we need to devise sampling in such a way by relating the Fourier transform of our sampled signal to the Fourier transform of our continuous signal or original signal. It can be performed in this way. This is our Fourier transform representation. Okay, now by substituting the previous value of xt, we get this. Then by exchanging the value of integrated summation, we get this values. Okay, now continuing, after we get the final value after evaluation, this one. But the problem with this value is that we have previously stated that for sampling frequency domain, we have to find the correlation between the frequency transform of this sampled and our original signal, and it should be in frequency domain. But here we obtained it in the form of time domain also. Okay, so but alternate version of this Fourier transform can also be performed. We will see next. For now, let us consider this formula to be in our mind. We will use this formula next. Okay, now as we have seen how the multiplication leads to the sampled signal formation in time domain, but in frequency domain we use the convolution for the multiplication, because as we move from time domain to frequency domain, the multiplication converts to the convolution, and it can be represented by this symbol. Okay, but now here the unknown is s omega. In order to find s omega, or to find the spectrum of impulse train, we will move forward. Okay, so here our impulse train, and for impulse train this is our Fourier series. Okay, so we have to basically form the Fourier transform of our impulse train. So we will, by moving forward, we will calculate sk, which is the Fourier series coefficient, which can be performed in this way. Okay, now Fourier series coefficient can be calculated, okay, for taking this impulse function, okay, which we have defined for st. Okay, then moving forward we get our Fourier series coefficient in this way. By substituting the value in this equation, we get our equation in this one. Now further elaborating it, now we have to here give the value of Fourier transform of our exponential function, which are elaborated in this way. Now by substituting the value for the general equation of Fourier transform, we will get the value of impulse train Fourier transform, this one. Okay, substituting the value in the previous equation for previously defined in frequency domain, we get this one. The final value is this one. Now in this value we can see that it is similar to our time domain time domain. Okay, the spectrum fixation is similar to the time domain in such a way. The only difference is that there we have Ts sampling period, here we are omega as sampling frequency. Okay, now it can be defined as the Fourier transform of the sample signal defined as the infinite sum of shifted version of original signal ft. Okay, now it repeats, the signal repeats after the integral multiplier of omega s, so omega s can be treated as a period. Okay, now taking the detailed expression for our xs or sampled in frequency domain, we obtain these graphs. Okay, for k is 0, k is equal to 1, or k is equal to -1. Okay, this is the complete graph that we obtained it, and we can see that omega s minus omega is greater than omega n. So by this condition we get our general condition, and if this tends to 0, or omega s minus omega n is equal to 2, we guess omega s is equal to 2 omega n. Now moving forward, now we will define the Fourier transform for digital signals. Okay, so general equation goes as follows. As we have seen previously defined this equation, which I told you to keep it in mind, we will devise the relation between this one and this Fourier transform in terms of frequency domain 1. As we will equate the both equation, we will get this general equation, but here the problem is that it is defined in both frequency and time domain. To keep it in frequency domain, we can replace omega with omega by Ts. Now here the left hand side represents the Fourier transform of delta signal and right hand side represents shifted and scale replica of omega s of the analog signal, which we get by sampling operation. Now moving forward, what are the basic conditions one need to remember in terms of sampling? The sampling, as I told previously, that the sampling frequency is very important. Here also we will discuss about the importance of the sampling frequency and also the sampling period. Now, as we know that as Ts increases, omega s decreases. Also, the shifted replica of this Fourier transform original signal move closer together. For example, it is the general condition as we have obtained previously. For example, if we condition omega s is equal to 3 omega n, okay, which increases omega s, as we increase omega s, Ts decreases and a large number of data is stored, which is proceed beyond necessity, and we get this extra sampling in this frequency domain, okay, which need to the data beyond storage. Now if we take omega s to omega 1, which will be perfectly sampled, and this particular extra frequency domain thing will be tends to 0. Okay, now if we decrease the omega s, the Ts will increase and it will lead to loss of information about the detailed signal. Okay, signal details, which leads to overlap. We will discuss further. Here we are seeing the omega s and omega n less than omega n, which leads to the overlapping, and it can lead to this overlapping, thus the destruction of the reconstruction of x3 from xn. Okay, for the data as a mean we can't reconstruct our signal if it leads to overlapping. So one important condition we must remember that omega should be greater than 2 omega. Next we will discuss about the spectrum of omega s, x3 or original signal and DTFT of the sampled signal. Now by taking the DTFT of the discrete signal, we get the general equation by this one. It has this phi as the DTFT frequency. Now we can divide the relation between this phi and our previously defined discrete frequency by Fourier transform of our discrete signal in such a way that we can generalize it for this discrete frequency tau is equal to omega Ts, and we can further evaluate it as follows. Now also omega s tau is just the frequency scale version of omega n, okay, and omega s this for this DTFT, this frequency is defined by this formula. Now alternatively, the effect of sampling may be thought of normalization of the frequency range, so that the frequency of continuous time signal should be equal to sampling frequency. It leads to the normalization of this DTFT frequency to 2 pi. So the period become 2 pi. So it can be plotted in this way for corresponding FTs of S omega as we have seen previously. Okay, this is oversampling, and this is perfectly sampling S, and this is our oversampling. Sorry, it is undersampling, oversampling. Okay, and it's perfectly sampling. Now moving forward, as we have seen previously for our frequency domain for discrete signal, we have this general formula. In order to plot it, we will break it into components. We will first devise this formula for k is equal to 0, then we will plot it, and further for the rest of the graph we will plot this. For rest of the formula we will plot this graph. Okay, now moving forward, we get the graph in this way. Just the difference between the plot between in the frequency domain of signals and this signals is that we have here interval of 2 pi. Okay, in DTFT we have interval of 2 pi. Okay, that's the only signal difference. Okay, now we will talk about aliasing. Aliasing arises mainly because when this omega s minus omega n is greater than our omega n. Okay, it leads to overlapping, and after overlapping we can't reconstruct our sampled signals in terms of original signals. So the definition goes as follows, that the unknown signal cannot be reconstructed due to insufficient number of received signals or partially reconstructed. Also, the aliasing leads to the phenomena of high frequency taking over the identity of low frequency one. Okay, it distorts the original continuous time signals. Okay, the signals changes from triangle 1 to 1. This also take this continuous form. It's not perfectly triangle, it distorts its shape. Okay, now also it distorts the 1 to 1 correspondence of the original time signals. Okay, so we can't construct our original time signal, so one must always remember this particular condition for sampling. Now we'll discuss about the MATLAB code that will be used for the visualization of our sampled signal. Here we have continuous time signal with a frequency of 10 kHz and sample frequency of very high 250 kHz. As we can see here, the graphical representation of a continuous sinusoidal signal. And if we want to have the discrete time signal of this particular continuous time signal that we have defined previously for different frequency, but different frequency means for different sampling rates. For example, 50 kHz, 20 kHz and 10 kHz. As we know that for our signal, the sampling frequency, our signal frequency is given by 10 kHz, and by sampling condition, sampling frequency should lie in this range or should follow this condition. Okay, so we will see what happens when one fall in the condition, and what happens if one violates it, and for overlapping we will see what happens. Okay, so here is a graphical representation. As you can see, the discrete time signals for 50 kHz, as we can see, it is defined at many points, but as you will see, it also defined at the points it is defined not at any particular discrete point, but at various points too. For example, here, okay, for example here, as you can see here. But if we are perfectly sampled it, okay, so if we are using this one, if we are using for 50 kHz, then we will be using extra frequency domain. Okay, but if you will do perfect one, we will just find at perfect place in discrete signal. Okay, now for discrete signal, for in condition for frequency range 10 kHz, which violates our condition of sampling frequency, then we can see that it doesn't passes enough data, or the data is lost in the system. Okay, now I had come to the end of my discussion. Okay, so here is a summary of all we have discussed until now in time domain and in frequency domain. As we can see, the formulas that we have used until so far, which can be easily seen here. Okay, so this is how I end my presentation. Thank you.